I think I will get started. It seems like there's at least a few people hanging out. Uh, I am Harry. If you don't know me, I'm Harry Goldstein. I'm a third year PhD student at the University of Pennsylvania. I work with Benjamin Pierce on property based testing and all sorts of other things. Um, I have been doing Haskell for about 5 years. I co teach, I TA a course for in Haskell with Stephanie Wyrick, CS 552 at Penn. It's a really great course. If you go on the course website, the materials I think are public if you're just curious to take a look. And this stream I'm doing this for two reasons. First, because I want to try streaming. I think it's an interesting thing to do, especially given the state of the world. And I had a kind of an extra lecture that I wanted to give during that course this past semester that I didn't have a chance to fit in. So I get to sort of do that here and learn about streaming at the same time. So I hope you enjoy. Thanks for being along for the ride. And please let me know in chat if I'm going too fast or too slow. I wasn't really sure who's going to show up, so it's hard to gauge the audience. And if you have questions, I do have the chat open, so hopefully I'll pay enough attention. So today we're going to go through, I'm going to assume you know what regular expressions are, but we're going to do a quick recap of how to represent them in Haskell. We're going to talk about Brzezowski derivatives of regular expressions, which are a neat way to work with regular expressions that are a bit more of a programming languages theory-y take on the whole thing versus the more theory A perspective. And then I'm going to show you a regular expression to DFA translation that is really neat and it's really cool. If you've seen Connell Elliott's talk at ICFP 21, then you've probably seen things like this, but you haven't seen them in Haskell. You haven't seen them done with live coding. So don't spoil it if you know where this is going. So here we've got a Haskell file, and we're going to start off by just defining our type of regular expression. So the type, obviously, oh, hi, Lef. We can have an empty regular expression. So we're going to call that void. That's the simplest regular expression, accepts nothing. If we want to accept a character, I'm going to call that lit. I've seen other things, but we're going to call that lit. It's just saying this regular expression accepts only a single character. Then for regular expressions, you need alternation. You need to be able to say this thing or that thing. And so I'm going to call that alt, and it's going to take two expressions as arguments. So this is saying, either the left one or the right one. It's going to match both. Then we want concatenation. So take two regular expressions and put them together. So if you want to accept the string AB, you take the expression A and concatenate it with the expression B. And finally, we have star. The cleany star, which does iteration. It can match the expression over and over and over again. I am going to deriving show. Maybe econ ord will be helpful too. This is generally what I do. So let's build an example just so we know what we're doing here. Maybe we want the expression A, B star plus C. Right? This is saying match A and then as many B's as you want or a C. And how do I write that? Well, that's going to be lit A cat star lit B alt lit C. And I will add a signature because I don't like warnings. And you can continue like this. But in general, we're actually not going to want to build expressions exactly this way. We're going to use smart constructors. So this is a thing that I don't know if everyone does in Haskell, but I certainly do whenever it's useful, is instead of building things with the constructors of the data type, you build things with functions that maybe do something else for you, make your life a little bit easier. And in this case, what smart constructors are going to help us do is tighten the expressions up a little bit, and they become an efficiency concern later, which I'm not worrying about efficiency really at all in this stream, but if you ever want to actually use these, you're going to care about smart constructors. So let's see what these look like. For alternation, right, we want to define a function that does alternation. And obviously, you could just take an xy and return alt xy. But we haven't gained anything here. The actual benefit is that alt of void y, well, that's just y, right? If you have an empty expression or y, you just have y. And similarly, if I have x or void, I just have x. Correct. Smart constructor is not a specific Haskell feature. It's a pattern that turns out to be very useful in any functional language. But one place it came up in 552 that we really wanted to emphasize is when you're building, if you know about AVL trees. So when you build an AVL tree is a balanced binary search tree that caches the height at the node. It caches the height of a node like in the structure. And it turns out that you always can just, when you build a node, insert the height in the same way by looking at its children and taking the maximum of their heights and adding 1. And what we did was we encouraged the students to write a smart constructor that computes that height automatically, that does that for them. In this case, the smart constructor is actually doing something for you that is saving on algorithmic efficiency. But in general, it's just this pattern of replacing your constructor with a function that does some simplification or something else that helps your code, that cleans up your code. Good question, thank you. For concatenation, I'm going to use some Haskell-y stuff. I'm going to make an instance of semigroup for regular expression. And you don't have to really worry about, there's laws that go along with semigroup. If you've never heard of semigroup, don't worry about it. The main thing is you get this function diamond, and we can just call that, diamond xy is cat xy. But we can do more, right? In particular, void cat with anything is void, right? If I concatenate the empty string with anything, I get void. And also on the other side, the same thing. And then, if you want to see something else fancy and Haskell-y, we're going to do a pattern synonym. Because notice up here, I didn't define the empty regular expression, right? The regular expression that matches the empty string. And we can get that by just doing star void. So star void, and I'll add a signature, is the regular expression that matches the empty string. If you think about it, star accepts the empty string or as many iterations of the argument as possible, as you'd like, and in particular that means it has to accept the empty string. And with this new pattern empty, we can also say that if I match x with empty, well, that's x, and empty with y is y. So this is just a kind of neat trick. It's gonna get rid of a bunch of cruft in our representation that we don't need, and we get to use a nice infix operator instead of having to do this infixifying of the constructor up here. So I can also I can write x1 as now lit a with concat with star lit b alt lit c. And in this case, we actually haven't gained anything because I wrote a simple expression to begin with. But in general, if you have a complex expression, or as we'll see, if you're building one algorithmically, you'll get some simplification from that. I'm not going to go too crazy with smart constructors now. I'm gonna write one for star, but I'm just gonna make it do nothing interesting. There are interesting things you can do with star. If you look, I think Michael Greenberg has a blog post on smart constructors for regular expressions. It's not what I want to focus on here. So if you were going to do this for real, you'd want to work a little bit harder on your smart constructors to make sure they're doing the maximum simplification possible. I'm gonna assume that all makes sense up to here, and I'm gonna talk about derivatives. I'm gonna do a quick sketch. Let's see if this works. Technology. Ready for this. Oh boy. Now we've got an iPad. Okay, so let's take the expression that we had. B star plus C. And we're going to define an operation, delta, which takes a character and a regular expression and gives you a new regular expression. And the way you should think about this is delta C is the expression with C removed from the front. That is to say, our expression accepts C and then accepts the rest of whatever R was going to accept. Let's do an example here. So we'll take the derivative with respect to A of our expression A, B star plus C. Well, because we want to take A off the front, we want to sort of already have matched A. That just equals B star plus C. And we can do this again. We can kind of keep taking derivatives. By the way, the derivative of the derivative with respect to B of this is the empty regular expression. You can't match. Right, so we can take another derivative. So now let's take the derivative with respect to B of B star plus C. And that's just B star. And the reason is, once you take a B off of this, it can't be the plus C part anymore. And so you just have B star left. But you can take as many B's as you want off the front of a B star. Anyway, yes. I hope this explanation of derivative makes sense. I'll keep going through the intuition as we define the operation. Okay. So let's switch back to Haskell and try to implement one of these derivatives. Yes, if you do have the post title, that's a good idea. So like I said, the derivative operation should take a character and a regular expression and give me a regular expression. And if you have the most modern version of Haskell's language server, you can do this, which is split on x, which is so cool. I did not know that this was a thing that just worked. So if you write Haskell and didn't know that that's a thing, that's a thing. So let's look at the derivative of void. Well, that's just always void. You can never take a character off of a regular expression, off of a void, so it's void. We'll do this by cases. So if c is equal to c prime, then the derivative of the literal is the empty string, because it's accepted it and now it accepts no more characters. Otherwise, it's void. This is right. So the derivative with respect to c of c is c, but the derivative of a with respect to c is void. For alternation, I'm going to just quickly change these variables for consistency. The alternation is just the alternation of the derivative. The derivative kind of commutes with alternation. The way to think about this is taking a character off of the front of an or is the same thing as taking the character off the front of the first, or, oh shoot. We are just pressing on. Okay. Let me just write this thing. Good. Derivative commutes with alternation. Perfect. We're going to skip to star for a second. This is let's see, x. I'm not sure I'm qualified to do a stream on how to set up Haskell LSP. I've managed it for myself, but I'm not sure I could do it for others. But maybe Lev. Derivative of a star, right? Take an a off of the regular expression. Then you have to deal with the rest of that first expression, and then you can continue with as many more iterations as you'd like. The thing with concatenation is a little bit tricky. So clearly, the first way to look at this, well, derivative of you can take the derivative of the first thing and then continue with the second thing. That's a good kind of normal case that makes a lot of sense. But there's another case that you have to deal with, because if I want to take a character off the front of a regular expression and the first expression, the x, can accept the empty string, then I also need to think about taking the character off the front of the second expression. So there's another case here, and I'm going to express that with an alternation. And I'm going to say if nullable, right? If x is nullable, if x can accept the empty string, which we'll define in a second. If x is nullable, then I also want to consider the derivative of y. Otherwise, we can just consider that case void. And now we'll define nullable. And we're going to do, I'm going to go a little bit quickly here and just, again, split on x. And is void nullable? No. Is a literal nullable? No. Is an alternation nullable? If either of its arguments are nullable. Is a concatenation nullable if both of its arguments are nullable? Right? Because if x can accept the empty string and y can accept the empty string, then the whole thing can accept the empty string. And star can always, because that's by definition. And so great. We have defined the derivative operation on expressions, and let's look at the example. So let's do that, and we can say derive with respect to a of example 1. And it's exactly what I said, right? It's you've removed the a from the front, and now it's just alternation with b and c, b star and c. And if I further take the derivative with respect to b of that, well, now it's just b star. And the other thing I showed was if I take the derivative of b of example 1, that's empty. So it's doing the thing that we wanted all along. It's saying how to kind of accept a character and then continue with the rest of the regular expression. Oh, actually, let's very quickly show how to use these derivatives. You can use them to check if a regular expression matches a string. So I can write match, which says string, and match is going to be, I think, fold-L. Fold-L deriv xx. Not flip deriv. I'm gonna have to think about this. Oh. Good. I went through that quickly because I want to get to other things. I can go over it more at the end if there's questions. But the basic idea is you go down the whole string, taking the derivative with respect to each character in turn, and then it determines if the whole expression accepts. So we can reload and we can ask, does a b b b b b match expression 1? And the answer is true. What about AC? Yes as well. But what about A, B, B, C? No, because that's not actually in the language of the string. Okay. Cool. Good. I expect people have seen this for the most part, and if you haven't, I'm happy to discuss more with you. This is a thing that blew my mind early on, because I think regular expressions, when they were first presented to me, were presented in terms of, oh, this is kind of a thing that's related to finite automata, and it was very much couched in theory, like theory A theory. And when I saw derivatives, I was like, oh, there's something. These are inductive definitions. There's something that feels more PL-y here, and it works better with my brain. So I tend to like this this kind of thing. So next, I'm going to switch over and I'm going to show a translation from these two DFAs, and I'm going to use a kind of non-standard presentation of DFAs. So I'm going to draw out what I mean again. Normally, the DFA that we had before, this works because void folds up nicely as the base case. Yes. Yeah, so other interpreters for DFAs, the thing that derivatives do well that the naive interpreter you might write does less well is the concatenation case and the star case, but mostly the concatenation case. Because if I just take a string and ask, does this string match this regular expression, you kind of have to decide where to split the string in order to try to match a concatenation. And the derivative handles that more cleanly than if you were to try to do it other ways, which is why this is a neat way to go. Okay, so the DFA for the thing that we looked at before looks something like this. It's a little bit messy. I'm not going to draw this sync state. We're gonna look at the states that matter. So this is how we would write the expression a DFA that matches the language A, B star plus C. And if I were to represent this as is in Haskell, I'd have to do something a little bit funky because there's a loop here, and Haskell doesn't like defining loops in data structures, at least not explicitly via pointers or something like that. So we're going to play a little trick, and we're instead going to define it to look like this. We're going to define it as co-inductive. We're going to define it as a kind of infinite tree that unrolls the loop as far as you ever could want to unfold it. This makes it not so much of a finite automata. It changes it from a deterministic finite automaton to a deterministic finitely generated automaton. But it's still it's still finite morally. So I'm gonna let it slide. I hope you will too. So we're gonna define our DFA to look like this. To look like this instead of like this, because it's nicer for some things in Haskell. Let's swap over to a new file, and we're gonna call it dfa.hs. Let's grab my language extensions and things. Okay. We're gonna have a DFA, and it's gonna be a record with two functions. One is going to be accepting, which is a bool, and another is going to be next, which takes a character and gives you a new DFA. Now, this is different from what you'll see. By the way, the record syntax may be a little confusing. Remember that accepting is actually a function from DFA to bool. And we should think of this as this DFA type is actually the type of states of the DFA. So it takes a state and tells us, is that accepting? And then next takes a DFA and a character and gives us and tells us the next state. It takes a state and tells us the next state that we're going to. We're just defining it as this. We're leaving the states implicit. We're leaving the alphabet implicit. We're playing a little fast and loose. But I hope at the end, when it all turns out pretty, you'll forgive me for that. We can write the DFA, our example 1 DFA again, this time as a DFA. So we'll do the thing that I showed before. So we're going to have states start, which is going to be a DFA. Accepting is false. And next says C equals A. Fail. So now we're going to have fail, which is a DFA state that is accepting, is false. Next is going to be const fail. This fail state has a loop in it, right? Its next is always itself. And that's just saying that once you get there, there's no way out. It's kind of a black hole in the DFA. So now if we're at X, so now we've accepted an A, and now we want to go to either the C or the B. So let's make Y and Z. So X says accepting is actually going to be false still. And next is going to be if C equals B, then Y else Z. Okay, I'll switch back quickly to the iPad so that we can see how these line up. Unfortunately, I didn't do a view where you can see them side by side. But let's look at this one. We've got really four main states here plus the fail state, right? So there's the start state, there's the state that I'm calling X, the state that I'm calling Y, and the state that I'm calling Z. And when I swap back over to here, we can see that we've got the start state that transitions out from A, otherwise it fails. Then, actually, I did this wrong. Then Y else if C equals C, then Z else fail. Right, so now if we've got B, then I'm going to go to Y. Nope. C go to Y. B go to Z. Otherwise fail. If we're in Y, we've accepted AC. Now we're going to accept, but if we see anything else, we're going to fail. That. Great. I hope this makes sense. These are kind of annoying to construct this way, so that's why we're not going to always be constructing these this way. But we can use this DFA. We can run this DFA. Run DFA is going to take a string and a DFA and gives us a Boolean. So run DFA on the empty string. Let's say A. This says, right? So if we have no characters left, then we'd better be at an accepting state. Otherwise, we should run DFA of next AX on X's. And just to prove to you that this actually works, let's run DFA on the string ABBB of X1, and we get true. What if I throw a C in there? Oops. Shouldn't be const Z. There we go. Oops. Good. So now we can run this DFA. Okay. I promised you a regular expression DFA conversion, and we're going to do it by converting every operation individually. So convert DFA to regx. Sorry, regular expression to DFA. So let's do void first. This is going to be a DFA. This is going to be our fail state, right? This is going to be the same thing that we did for our fail state. So great. Except it should be not fail, it should be void. Perfect. How about lit? Well, it's also not an accepting state. And now we want to say that if so Liao, I did point this out before. They are finitely generated. They are not finite, but they are, because co-induction, they are finitely generated. So I hope you'll allow me this slight abusive terminology. Then so I've done a little bit of a. We're not gonna write an empty explicitly, but remember that empty is star void. We're basically saying that if thanks Leah, thanks, I appreciate the forgiveness. So in order to accept a literal, we're gonna give a state. That state is not accepting, but then if we do get the literal, the next state should be accepting. And if we get the character we're hoping for, the next state should be accepting. Otherwise, the next state should be our void state. And by the next state should be accepting, we're going to use star void. We're going to encode the empty string in the same way that we did before. Now let's look at a kind of interesting case for alternation. And this is a little tough sometimes to wrap your brain around, but we'll do it. So, and this is also where I think, I hope some of you might start seeing some patterns, or you might already have. But when is a DFA of an alternation accepting? Well, it's accepting if either of the arguments are accepting. So how do I get my next state here? Well, I get my next state by taking the next of either of my arguments. And I've already shown how to how to kind of shove two DFA states together. That's what we're defining here. So what we're going to do is we're going to recursively apply alt to the next of xc next YC. Right? We're saying in order to take a C step, in order to do a C transition from an alternation, I'm going to take a C transition in either of the arguments and put them together with another alternation. And this is going to have the effect of kind of recursively zipping the trees together, zipping the DFAs together. That one's a little tricky, but I hope it makes some sense. Let's do concatenation. Well, a concatenation is accepting if both of the DFAs that build it up are accepting. So there's an and there. And then we want to sort of think about this as, how do I take a step into a concatenation? Well, I'm going to take a step into the first one. So I'm going to say that take a next and then concatenate that with the second. But there's a similar thing to what we saw before, which is that, well, what if we want to take a step into a concatenation, but the first DFA could accept, could have just accepted, right? What we're trying to do here is, if you look at this tree again, with a concatenation, what we kind of want to do is put take another tree and insert it at each of the, sorry, let me grab my pencil. Insert it at each of the accepting nodes, because that's where you can continue from, right? You're accepting, like once you've gone through a tree, you've got to an accepting node. Now you sort of want to continue on with some other tree. And so we can go back here and we can say, well, alternatively, if accepting X, then we actually want next YC, else we can just do void there. And to bring this home, well, a star is always accepting, and we want to do next. And a star is going to sort of want to loop on itself. You're gonna take a step in, and then you're gonna loop. So XC with cat of X. So I'm going to just clean up these definitions for a second while I wait to see if there's questions in the chat. I know that went a little fast. We're getting near the end of time, so I don't want to go too far over. But I hope some or maybe all of you will have noticed at this point that I kind of just did the same thing twice. So if I go back and I look at my regular expression and I look at my definition for the derivative, it looks an awful lot like all the definitions for next for the DFA. And if I do that with nullable, it looks a lot like the definitions for accepting for the DFA. So what's going on here? Well, this is a thing that the way that Connell Elliott puts it in his ICFP talk is that if we consider the derivative that we wrote here to be a symbolic derivative, like in algebra how you take x squared and you turn that into 2x, then the DFA perspective is like doing automatic differentiation in like PyTorch or something like that. And the critical thing is that while it feels like on one side of things we're manipulating syntax, right? A derivative is a very syntactic operation on one side here. But then on the other side, it feels like we're building up trees. It's a little less clear where the syntax nature of things comes in. Although syntax is just a tree. Anyway. But I think that this is really cool that there's two ways to get to basically exactly the same code. And this is actually up to like renaming exactly the same code. And I think it's really cool that you could have arrived at this in the same way, in two different ways, arrived to the same code. The thing that I wrote up here with run DFA, I explicitly avoided writing it with a fold, but if you write it with a fold, it looks exactly like what I did before. So yes, takeaways here. Regular expression derivatives are a super cool way to work with regular expressions, to manipulate regular expressions. And there's another perspective on them, which is as these co-inductive DFAs, or what Connell says in his talk is co-inductive tries. And they're really two sides of the same coin, and you can kind of play those perspectives back and forth, and there's a lot to gain from that. Ed asks, I'm curious, are these the same in performance, code size, whatever? I believe, I'm not 100% sure, but I believe as long as you set up your smart constructors properly, these are equivalent. In a way, they really are actually the same code, because I mean, they are like actually the same code. The only thing that could get you is if your regular expression blows up while you're taking its derivative, because you've got too much cruft in there, because the smart constructors aren't normalizing well enough. The DFA perspective does that normalization automatically for you because it's really actually normalization. Whereas in the derivative case, you could get into a situation where your syntax is blowing up. But I believe that as long as your smart constructors are smart enough and do as much crunching down as possible, then these are really doing the same thing. There may be a small memory effect. It's hard to know with laziness and all of that. It's tempting to think of the DFAs as kind of pre-computing derivatives, but because of laziness, they're really not, as far as I can tell anyway. I don't want to make too grand claims there because lazy cost analysis is hard. Hey, Editing Harry here. After this point in the stream, I mostly just rambled, so I'm going to cut it here, but the main takeaway is that regular expressions are cool and the derivatives are really useful. If you want to see more content like this in the future, just let me know. You can reach out to me on Twitter or on YouTube. And otherwise, thank you for watching.